Good morning. Thank you guys for coming to this introduction to the Ohio Supercomputer Center workshop. I am Amy Latessa, and I work for UC IT, Information Technologies. We host many computational workshops throughout the year, so check our website. And we bring Ohio Supercomputer representatives here once every semester. So this is the fall semester training. The morning is the intro. The afternoon session will be over in Baldwin Library, the CES library, and it's actually big data. So you get in and do a little more compute. If you have questions about today and getting accounts, how to get on and keep on, you can reach out to me. I have business cards over there. And we have a good partnership with OSC. Like I said, Dr. Tom Beck from chemistry was the chair for the past term. He's not anymore, but so we have good connections and they're a great resource. So thank you for coming. And this is Brian Guilfoos, and he'll be teaching the class this morning.
All right, thanks, Amy. I'm from the Ohio Supercomputer Center. Name's Brian Guilfoos. We'll talk a little bit more about my background. I know I saw the sign-in sheet, most of your chemistry and the mechanical engineering folk. Heavy supercompute users, if you look at our total statistics, those are two heavily represented areas. So I'm sure you're going to be able to take advantage of us. Please ask questions at any point, especially because we have such a small group. It'll be very easy to deal with those. We'll just be kind of relaxed and informal. We'll go through the slides, and any questions you guys have, just fire them off, and we'll try to address them. So this is our Computing Services to Accelerate Research and Innovation talk. This is kind of our introduction to OSC services, hardware, and environment. Are any of you current OSC users? No. Okay, good. And this is probably the perfect target audience for this slide deck. So as I mentioned, my name is Brian Guilfoos. I'm the HPC Client Services Manager at OSC. My team is the one that answers the help desk. So if you need account maintenance issues or you're having problems with any of our services, we're the first people that you're going to talk to. We may bring in other folks at the center to help deal with issues, but that's our primary role. We're going to talk about a couple of things today, what OSC is, a little bit about HPC. Have any of you used HPC resources before? No. Okay, perfect. A little bit about the hardware that we have, our data storage systems, what batch processing is, how to do it, how to access the software we have available, and an on-demand web portal demonstration if we have some time at the end. I think we probably will. So what is OSC? Basically, the Ohio Supercomputer Center was founded in 1987. We're a statewide resource for all universities in Ohio. So high performance computing services, computational science expertise. We primarily serve universities, but we also serve private industry. We're trying to advance the state economically. So we're funded through the Ohio Department of Higher Education. Because we're a statewide resource, we are actually on the state budget. So every 2 years, the state does an operating budget, and every other 2 years, they do a capital budget. We are a line item on both of those budgets, which means our budgets are subject to political pressure. That money goes through the Department of Higher Education. So my boss, the director of the center, he reports to the chancellor of the ODHE. We're located on OSU's West Campus, and OSU is our fiscal agent. So I'm an Ohio State employee. It makes it a little bit easier for us to work with Ohio State than if we weren't. But we are a statewide resource, and so we don't discriminate for or against any university in allocation policy or scheduling policy or anything like that. So you guys are equal partners and equal users of our services. We're actually bundled up in this thing called the Ohio Technology Consortium. So OSC is included in that group of organizations. We've kind of bound together for some cost savings measures at the state level. But also there is ORNet. ORNet is how UC connects to the internet. And they are in our building, so it's also how we connect, which means OrNet runs, a 100 gig fiber network here in the state of Ohio, and so you connect to that at very high speed. Traffic goes straight to us where we have a 40 gig connection to that network. So there's very high bandwidth connections between your campus and our data center, which makes it very easy to move large amounts of data in and out. And then OhioLink is there as well. OhioLink you may have heard of if you go to the libraries and you're looking for a resource and you see libraries don't have that resource. You can check the OhioLink catalog, which is connected to all the universities in Ohio that participate, including OSU and other large institutions, and it allows interlibrary loans, and so you can get resources from other institutions. They're also in our building. So if there's something that, if you're working with us and you're having some sort of issues moving your data back and forth, we can go across the hall, talk to OrNet, get their engineers involved. So the fact that we work closely with these other units is beneficial. We'll talk a little bit about the production capacity. I think we talk a little bit about who later, but this is a little bit about what. So 221 million core hours were used in calendar year 17, 78% average system utilization across our 3 production clusters, over 4.4 million jobs were run, 98% uptime. Our storage services, 44% average utilization, 1.5 petabytes of data stored there, 2 petabytes transferred in or out during 2017, and 79% of jobs started within 1 hour. So we have pretty good throughput. A lot of our that statistic, any aggregate statistic could be a little bit misleading, right? We have a lot of small single core jobs. And so those tend to get scheduled very quickly because they can be filled in little gaps. I'll talk about that a little bit later. While 79% of the jobs start within 1 hour, the average queue wait is a little bit longer than that, a little over an hour. I mentioned chemistry is a large user. They account for, chemistry users account for 23% of our core hour usage. Materials research, 26%, engineering, 18%. Those are the big disciplines that use us. Physics, 6%. They account for a significant percentage of the number of jobs, though, right? Because physicists like to run lots and lots of really tiny jobs. So 6% of the core hours, probably like 20% of the jobs. And we've seen a lot of growth recently in areas like biological, behavioral, and social sciences. And so it's interesting to see these other disciplines starting to work on problems that are too large or too complicated to do outside of a HPC environment. So we have several services that we offer. The ones I want to point out are the cluster computing. That's the one you probably are thinking about when you think about the Ohio Supercomputer Center. That's going to be our compute machines, the supercomputers. I'm going to spend a lot of time talking about those today. We also have a research data storage service. So we have high performance, large capacity data storage spaces. And we're expanding those services both in size and diversity. So we're adding different storage tiers in the near future. Education. So this is part of that educational mission, is going out and providing training to folks, but we're also involved in HPC education at the national level. And so we do a lot of activities in trying to get people educated about HPC and computing. Web software development, we have web developers in-house, and so one of the things I'm going to show later is something called OnDemand, which is our web portal to access HPC. It's based on an open source project that we run called OnDemand. There's now, I think, over 30 different institutions that have deployed their own copies, and so it's becoming a very common way to connect to HPC services. And it also allows app development, so you can take an HPC workflow and turn it into a web workflow. And I have some examples of that later. We have expertise on staff to do that. Certainly, it's an open source project, and we provide tools to let people build their own web apps. But if you have an idea for one that you want to make, we can help with that. And then scientific software development. So we have a lot of expertise on parallel computing on staff. And so if you have a code that you want to you need help getting it to scale out or scale up, we have some staff that can assist with that as well. So, let's talk a little bit about example projects and concepts, like why might you want to use HPC? You guys may have a decent idea about this, but it's an interesting thing to talk about. So right, your simulations or analysis take too long on your personal computer, right? This is a really common thing. Somebody will run a simulation on a laptop and then they find they can't do anything else with that machine without slowing down the compute that they want to do. The size of your data is too large to be contained, storage, or accessed memory on your computer, right? So if you just can't load your problem into memory on a laptop with 8 gigs of RAM, we have machines with 192 gigs of RAM. So we have memory available to help with that. You'd like to be afraid your system to do other tasks. That's the most common one. I think we've all seen lab computers with a sign on it that do not touch, right? Because it's being used for something. We can offload that work and let you do a lot more of it than what you might be able to do otherwise. And in particular software. So this is a niche, especially for some of your domains, where we can provide a lot of value. Things like Gaussian, expensive licenses. We buy licenses at the statewide level for all the universities to use, and that's a part of our services that can sometimes be overlooked. So I have a couple of examples of some interesting things that have been done at OSC. This particular one, Ian Howitt is the principal investigator. He's at the Ohio State University. He actually runs the Bird Polar Research Center at OSC. And he takes satellite images of glaciers and does analysis on those to kind of track what's happening with the glaciers over time. And he was able to use that same technology to look at satellite images of Nepal after the earthquake in 2015 to actually help direct resources in the recovery effort. Where are areas where additional aftershocks would be high risk for more damage or landslides? Where was there a lot of damage? Where do we need to direct resources? And actually, he worked with the federal government on that in providing aid to Nepal. It was a very interesting project. I think it was recently highlighted in the New York Times. So, and I should mention, by the way, your success stories are our success stories. And so being able to share these are really great for us, and it's also really great for you. And so we do want to know about the successes that you have had from using our services so that we can talk about those, because it helps convince the state legislature to continue to fund us. So treating nerve agent exposure, this is another OSU-based project. Basically, they're doing some biochemistry to identify how to block nerve agents from binding to molecules. That's Christopher Haddad. He actually chairs our allocations committee. And this is one that you probably would not have thought of, Pringles. So Procter & Gamble did this work at OSC. Apparently they were having a problem with the Pringles chips flying off the assembly line, and they had too high of a loss. So they wanted to optimize their manufacturing facility, so they did aerodynamics work on the Pringles chips to figure out how to redesign their line so they had less lost product in manufacturing. So that one's a little bit weird, but that kind of application, the idea, how do we make our production lines more efficient? How do we use less plastic? How do we use less metal? How do we design things more efficiently? That kind of thing happens in HPC all the time in the industry. And so this is a particularly interesting example. I'm actually going to skip this slide. So supercomputers become history quickly. And so I think this slide's a little bit dated, but it's still very illustrative of how fast HPC changes. So this is a Samsung phone, I think from 2015. We're going to compare it to a supercomputer from 1989, the first supercomputer OSC bought, which was a Cray YMP. I believe the fastest machine in the world at the time. This is a 2015 smartphone. So if we compare that to that Cray YMP, the cost, $740 for that phone, $20 million for the supercomputer, 4 gigs of memory on your phone, 128 megs on that old supercomputer, 64 gigs of storage on your phone versus 30 gigs on the supercomputer, and 302 gigaflops on your phone versus just 2 gigaflops on that supercomputer. So every single one of you has a phone in your pocket that is more powerful than the most powerful supercomputer in the world 30 years ago, right? So these things become obsolete fairly quickly. I'll talk about a computer we have that is approaching 6 years old. We're actually going to retire it later this year. And it's I think like a tenth of the supercomputing power of our newest supercomputer, uses more power, less efficiently, and it doesn't really make sense to even keep it running anymore. You can still do a lot of good science with that compute, right? But in terms of the economics of running the machine, it doesn't make a lot of sense because you can buy so much more for such a small amount of money that runs much more efficiently. Another thing that's important to keep in mind is scale. We used to just kind of display the table of scientific SI unit prefixes. That's not particularly useful to really get your mind wrapped around the scale of these things, right? So we talk about common sizes in computing. We say like kilobytes, right? That's about a cup of rice, right? About 1,000 grains of rice, about a cup of rice. A mega is about a barrel of rice. A giga, 3 truckloads of rice. A tera, and now we're talking about maybe our storage, our aggregate storage is measured in terabytes. 2 container ships worth of rice. Peta, now we're talking about the scale of our compute that we have at OSC, petaflops. Enough rice to cover New York City. And then the national scale is exa, right? Exaflops is kind of the highest level of supercomputing right now. That's enough rice to cover Texas, right? So it's easy to think, well, we're adding a bunch of zeros, but the scale of it is really, really large when we start talking about that stuff. So a few bits of terminology that will be useful both as we go through these slides and as you use OSC. A cluster is the term that we use for supercomputers now because they are groups of computers connected by a high-speed network. That Cray YMP was not a cluster, it was a single computer. So the architecture has changed. The dominant architecture is clusters right now. Now those clusters are getting, they're starting to look more and more, the individual nodes in those clusters are starting to look more and more like those old Cray YMPs, and that the core counts are getting very, very high. Right, 15 years ago, everything was single core, and now you get processors. If you think about like your home computer, 4 cores is very normal for a processor. We have 20 cores per processor and 2 processors per computer in our new supercomputer nodes. So we're up to 40 cores in a single box. Multi-threading is useful. We talk about nodes is what we call the each of those computers in the supercomputer, right? So we may have 800 nodes in a computer or 240 nodes in a computer. And each one of those is a high-end workstation of its own connected to the fiber network that makes up the cluster. Core, right? So the kind of common terminology differs a little bit from the electrical engineering terminology. Talk about cores on a processor, processors in a box. From our perspective, in terms of scheduling and accounting, a core is a core is a core. We don't care about what processor it's in. There's just so many per box. And we don't really think about processors at all. We just talk about cores. So you'll see that when we talk about some of the machines in a minute. And then flops, right? That's the other big thing, floating point operations per second. That's how we measure the speed of these machines. And then the other term that's important to know is GPU. I know there are chemistry codes that leverage GPUs, and we have a bunch, and we'll talk about that a little bit as well. So this is, I mentioned clusters, right? This is the structure of a supercomputer. You, the researcher, logs in either via the terminal or web portal, and you connect to login nodes. In this case, on the one we're showing here, there's just 2 login nodes, those 2 boxes there in the middle of the diagram. From there, you can access all of our storage services on the login nodes. So you can and I'll talk about why you use login nodes in more detail, but prepare your work there. The real compute is one layer deeper in all of the compute nodes. We have 684 in this particular cluster, each one with its own stack of cores and memory and local disk space, all of which are also connected to the storage services. So the environment looks the same on all of them, but when you run on the compute nodes, you're going to have dedicated resources, whereas the login nodes are shared. There may be 30 people logged into one of those at a time. Right, memory holds data that's being calculated on, as well as the computational instructions. So shared memory is local to one node and several processes. So on a node, each of those threads can access that shared memory, right? Just like a normal computer. Distributed memory is on multiple nodes, and each process has its own copy of the data. So if you want to run on multiple nodes, you get access to more memory, but now you have to manage where the data sits. You can no longer just allocate memory and put stuff in there and have the threads access the memory. If a thread on one machine needs access to data, a copy of it needs to exist on that machine. And unless you're using packages that handle that for you, it's a responsibility of the user to manage that data in your programming. Storage is another important component. There are different types of disk for different needs. There's a local disk in the node, often SSD at a lot of places. At OSC, they're standard disks currently. And that provides a local scratch space that doesn't have to go over the network, so you can stage your data there, and the performance is very good for read-writes on that host. There's shared scratch system, parallel file systems like Lustre, GPFS, tuned for high bandwidth, not high IOPS, right? So if you're writing lots and lots and lots of little files, it's not great. But if you're moving lots of data in and out, the performance is typically better. There may be a burst buffer layer in front of that. OSC has one that we're rolling out to clients with our new cluster in about a month, maybe a little longer. And that's short-term storage, that's scratch space, right? It's not backed up. If you store data there, it may stay there for a while. We don't actually remove data that is not being used until it's 120 days old. But if something were to happen to the file system because it's not backed up, that data's gone, right? So it's not permanent storage. And then we have longer term or archive storage available as well. So let's talk about some of the specific hardware that we have available. So we have 3 systems in operation. One is not shown here because we're retiring it in about a month and a half. Pitzer is our new system coming online right now. It's actually up and running. We are currently testing it. We expect to open it up to early users in about a week and a half, and then open it up to the general community sometime in November. Pitzer is about 1,300 teraflops. So 1.3 petaflops, Owens 1,600 teraflops, and Ruby 144 teraflops. The machine we're turning off is 150 teraflops. Number of nodes, Pitzer is a smaller computer in terms of nodes. It's only 260 instead of the 824 on Owens, and the 240 on Ruby, which has historically been our smallest system, and still actually still is. The core counts, though, this is where things get interesting. You look at Ruby, 4,800 cores and 240 nodes. Pitzer, a few more nodes, over twice as many cores, right? So the core count per machine is going up quite a bit. And because we have lots of serial workloads, lots of single core jobs, we can still, even with only 260 nodes, push a lot of work through this new machine. And then Owens is currently our large machine with over 23,000 cores. Total available memory, 70 terabytes on Pitzer, 120 on Owens, and 15 on Ruby. Memory per core, we try to keep that up, so we have a lot of memory available to all of these processes, especially these single core processes, and folks aren't stepping on each other too frequently. So over 5 gigs per core on Pitzer and Owens, a little bit less on Ruby. And then the interconnect, our 2 newest machines are both EDR and InfiniBand. So InfiniBand is a fiber network that we have. and it's FDR on Ruby, the older machine. So there's several different node types in these clusters as well. They're all roughly shaped the same. The proportions are a little bit different, and of course the hardware specifications are different. Owens, the large cluster that most of you will probably be using most of the time. There's 648 standard nodes, or dense compute nodes is what we also call those. Each one has 28 cores. What's the processor? Broadwell, I believe, or no, Haswell. I can't remember which one was the newer one. I think it's Haswell. Haswell processors and 128 gigs of RAM in each of those boxes, right? So individually, these are very powerful machines. We also have GPU nodes, and so there's 160 nodes with 28 cores per node and 128 gigs of memory, but also with NVIDIA GPUs, and I think I have the specifics of the GPUs a little bit later on. And so these nodes, even though there's only 160 of them, they about almost double the total compute of the system. And we have what we call data analytics nodes. And so we have 16 of these, 48 cores per node. So they're slightly different. It's a different processor and a slightly different architecture. These are the older Broadwell chips. 48 cores per node, 4 processors instead of the 2. They have 1.5 terabytes of RAM. So if you have really memory-intensive applications that can't be split across nodes, because that's the easy way to get, well, that's not the easy way. We have a lot of memory available that way. This is obviously easier, but it's harder to schedule on these because we only have 16 of them. So if you can run in parallel, great, take advantage of that. But if you can't, if your algorithm doesn't parallelize and you need a lot of memory, we do have some nodes available to address that. They also have 12 terabytes of local disk space as opposed to about 1 terabyte in the other nodes. So they're really designed for looking at large amounts of data. So when you stack all that up, this is kind of what the system looks like with 16 large memory nodes, 160 GPU nodes. Those are running NVIDIA Pascal GPUs. 6 debug nodes. So during the day, we have 6 regular compute nodes pulled aside for very small jobs. You can request to run in the debug queue and get turnaround that's a lot faster if you're trying to test jobs out. And then before you scale up and run in the larger queues on the production nodes. There's 4 login nodes in this particular system. And I mentioned there is a burst buffer IME in front of Scratch. That is in testing now. We expect to roll that out about the same time we roll Pitzer out. So these are the Pitzer specifications. This is the other. I should mention Ruby's not generally available. If there's a specific reason you need it, great, we can get you on there. But most of the time, it'll be Owens and Pitzer. That'll be interesting to you. So Pitzer, there's 224 of those of the standard nodes. They're Skylake processors, 40 cores per node, 192 gigs of memory, and 1 terabyte of local disk space. We only have 32 GPU nodes, right? The node counts are smaller because the nodes are much more expensive than they were on Owens. 32 GPU nodes. Each of those has 2 instead of 1, right? So Owens has 1 GPU per node. This one, they have 2 Volta V100s. Those are very good for machine learning applications. 384 gigs of memory and 1 terabyte of local disk space. And then we only have 4 large memory nodes on this machine. They're also running Skylake processors, just like the other 2 node types. 80 cores per node, 3 terabytes of RAM, and 1 terabyte of local disk space. So very, very expensive machines, those. So we only have 4. And 4 login nodes as well. And so this adds up to, it's about 800 teraflops of CPU compute, an additional 500 in the GPUs. I mentioned login nodes, and we have 4 of them for each of those machines we just looked at. Their purpose is to submit jobs as the batch system, right? Edit files, manage your files, submit jobs, small scale interactive work. Maybe you've run a large job and you just want to do a little bit of visualization on the results. You can do that on these login nodes, but they're shared. And because they're shared, we have to put some limits on the resources. 20 minutes of CPU time and 1 gig of memory. If you exceed either of those, the process will get killed automatically. So you really want to use the compute nodes for your heavy lifting. Any questions about the stuff I've covered so far? Okay. So let's talk a little bit about our data storage services. We actually have 4 different file systems. And I've talked about all of them, right? Well, almost all of them. So we have the local scratch space on each of the nodes. That's kind of the hidden storage service that's available everywhere. Every time you run a job, you have access to that local disk, and it's a stage data out to do work on it, copy your results back to one of the permanent file systems, and then that'll get wiped at the end of your job. And we have the broader parallel scratch file system available everywhere, common to all the nodes, right? So if you're working on more than one node, you write something in the file system, the other one can see that. It's not true of the local scratch. Those are independent to each computer. We have the project file system. The project is our long-term storage archive. So if you have a lot of data storage requirements beyond what we provide in home, you can get an allocation on project. That stuff is also backed up to tape. It's intended to be a persistent store of data. We have about 3.4 petabytes of storage there. We're planning to double that in the near future. And then home directories. Every account gets a home directory. We're pretty generous with quotas there. You get 500 gigs straight out of the gate, but we can't expand those, right? So if you need more than that amount of storage, you're going to have to get a project allocation for your research project on the project file system. Home, your files are stored here, backed up daily. You can use either $home or tilde username to reference the location. It works on all of our clusters. And by the way, the file systems are mounted everywhere. So you log into Pitzer and you create a file in your home directory. That same home directory is available on the other systems. We don't have unique home directories for each cluster you're on or anything like that. Project is available to project principal investigators by request, shared by all users on the project, backed up daily. That's under /fs/project, and then the project code. Scratch, large input or output files, faster I/O than home or project, but it's temporary and it's not backed up. And then Tipter, that's that local disk space I talked about, right? Storage on the compute nodes, but you have to make sure to copy any results back to home because all that data will disappear at the end of your job. So in summary, those are the 4 file systems. Those are the amount of space available to you or the limits on the space available to you is maybe a better way to put that. Whether or not it's backed up or not, and then whether or not we will delete data on those file systems. So as I mentioned before, Scratch, 120 days of inactivity on a file, we'll delete it. On those temporary directories, when the job's completed, we delete the data. So a few tips for managing that space. Even though we are very generous with home directories, people do bump up against those quotas eventually. You can compress large files. That's one way to deal with the space. If you're worried about running out the number of files, so we do have limits on the number of inodes available to you as well. It's 1 million files. You can use tar to tar those up. Doesn't save any space, but does free up inodes. And then project space, right? So you can go to your principal investigator and request project space, and that's one way to get more storage. We do report your quota in a lot of different places. When you log in, you will see information about your quotas. So it'll show, in this case, this is a little dated. We should probably update this slide. The top line there shows a home directory quota, right? 28 gigs of 500 and 41,000 files of 1 million. So that'll show up when you log in, kind of after message of the day. It shows your quota information. And there's an example there of a project quota as well. 27 gigs of quota, 27 gigs of a 5 terabyte quota, and 500,000 files of 1 million that are allowed. And you can also view those on OnDemand. When you go to OnDemand, it'll show you your quotas when you log in. However, this is not live data at exactly that moment. We cache this, I think, twice a day. It used to be once a day. I believe it's twice now. So if you're actively creating or deleting files and you log in, you're going to get a number that might be a little bit stale. So that's just something to keep in mind. All right, so let's talk about actually getting started. Since none of you have accounts, this is kind of an important section. Who can get a project? So a research project for academic users needs to have a principal investigator. So that's typically going to be a full-time faculty member or research scientist at an Ohio academic institution. If you do not qualify, you're going to need to get a sponsor who does to get access to the system. That PI can then authorize accounts for students, postdocs, collaborators. Those collaborators do not have to be at the same university. So if you're working with, or even in Ohio, right? So if you're working with somebody at University of Buffalo, for example, and they need access to this computer as part of your research project, they can get access. The same as if they were here at University of Cincinnati. That's authorized use. Classroom projects are also available. So if you wanted to leverage OSC in teaching a class about computational science, we can provide accounts and resources to do that, including coming and giving a version of this talk to the students to explain what a supercomputer is and how to use it. These are offered at no cost to academic users. There's a caveat with that I should explain. A certain amount of modest usage is fully subsidized per year. So per fiscal year, up to 10,000 resource units. I don't think I really talk about how that math is done, but it's a fairly substantial amount of usage in the sense that 80% of our research projects per year don't cross that threshold. So it's bigger users that will run into this. Once you get past 10,000 RU, this is the current model. There is a fee that's assessed to your institution. So UC will get a bill for usage. It is still heavily subsidized, well below market rate kind of a bill. But UC does get a bill for large usage, and so that may need to be paid. I'm not sure what the model is at UC, whether it's being picked up centrally or whether the department's responsible or whether the principal investigator is responsible. It's different at every institution that's involved. So that's something to keep in mind if you're going to be doing a lot of research at OSC. We also support commercial use, right? So commercial organizations just purchase time from OSC at market rates. So a few terms that are important. Projects, so I've referred to these a bunch of times. Headed by a PI, includes multiple users. One or more users can include quite a few. It's a basis for accounting. So when you are on a project, you charge jobs against that project's balance, right? And then that's how we do the accounting. You may have multiple projects, and so you may be able to choose which project to charge a job to depending on who the work is for. And you submit proposals for computing resources. So we actually have a grants process that is involved in making sure that the academic use of the center, because it is still heavily subsidized by the state, is responsible, right? So you'll have to submit a proposal, goes out for peer review, and then an allocations committee makes those allocations. Our allocation rate is very high, right? This is not as onerous as submitting for an exceed allocation, where they tend to not award a huge ton of projects and then tend to under reward those, or applying for an NSF grant where the award rates are low, right? I think 28% on NSF grants. Ours is north of 90%, so it's not super onerous. And then the other term is the account, right? So that's the username and password to access your HPC systems. That's typically what we call an account. Each account is used by one person. This is especially important for data security and audit and tracking all that kind of stuff. So please don't share accounts. If you work on multiple projects, you will have one account that can access all of those, right? So you'll get one account when you start at OSC, And if you get added additional projects in the future and removed off your current one, you'll be able to charge to those different projects for it. I mentioned resource units a minute ago. Charges are in terms of resource units. So on Owens, one resource unit is 10 CPU hours. And so 10 core hours, essentially, right? So if you use 10 cores, so those are 20 core nodes on Owens. If you use a full node for half of an hour, that's 1 RU, right? So you can then kind of extrapolate out to see how many core hours you can get on that machine before you have to worry about charges being accrued. Currently, we do not charge but at anything other than the core hour rate for GPUs, right? So GPUs are actually free. You just get charged for the host processor time associated with those GPUs. Large memory, there's also no additional surcharge for the large memory nodes. There's just more cores in that node, and you're going to take the whole node. So you're going to get charged a higher number of core hours, even if you're not using those cores to access those large memory nodes, but there's no additional surplus for using those, or additional fee. Oakley and Ruby, the older machines, Oakley, again, being turned off in less than 2 months, most likely. One resource unit is 24 hours. Because the machines are less capable, we've discounted them to be cheaper. And as I mentioned, CPU hours, wall time, times number of cores requested. So you get your allocation in terms of RUs, but you can run those anywhere. Now, we don't have the charging figured out for the new machine yet, so I can't tell you what the core hour rate is going to be for those. We will probably be adding charging for GPUs on that machine and memory on that machine at different rates than the base core hour rate. So, but once we get that information, we'll share it on the. Once we figure it out, we'll share it on our website. So you get an allocation at OSC that can be used across any of the clusters at the different rates. So you don't. Lots of other centers, you get an allocation on a particular machine, and if you want to use a different machine, you have to actually convert those to different units and then apply to get those moved to a different machine. You just run anywhere at OSC, whatever you can leverage. If the queue weights are lower on an older machine, and the software is there for you to run, and you can tolerate the slower performance but the cheaper cost, you can bounce over that machine and run there. And as I mentioned, those jobs are charged against a project running down that allocation balance. Okay, I talked about this already, actually. Fee structure. So the first 10,000 RUs on a project are subsidized. Usage above 10,000 RUs, we build the PI's institution at 7.5 cents per RU. And PI should contact their Office of Research for details on local billing. So if you think you're going to be above this threshold, you should talk to IT here. To understand, or the Office of Research, to understand how that might impact you. All right, so this is actually, so all of that stuff gone. How do you get a project? Well, if you're eligible, you can go to this URL here, Supercomputing Support Account, and apply for a startup grant. So 1 per PI per lifetime, so if you've never used OSC before, or you're a new principal investigator in Ohio, you can sign up for a startup project. Basically, you tell us who you are, what institution you're with, what department you're with, your contact information, and we turn around and hand you 5,000 RUs, no questions asked. It's seed. It's a seed money, seed RU to get you started. So you can just pop on real quick and start investigating your project to see how many RU am I really going to need. I can run some benchmarks. The idea is to use this for testing to prepare for your first proposal. Once you exhaust that RU, we will ask you to submit a proposal to continue computing. Those allocations can be added to that project, so you can ask for a standard award of 10,000 RU, a major of 30,000, or discovery, which is above 30,000. And the more you ask for, and we've had people ask for like 1 million RU, the more you ask for, the more detail you need to provide about your science and your justification for the size of the award. If you're asking for 1 million RU, the allocations committee is going to look really closely at what you're asking for. Is all of that compute going to be done efficiently? is your request reasonable in size? Can you make improvements to the code, reduce the amount of RU you need so you can run more efficiently? Because that's a substantial amount of the service. 10,000 RU is not that much, and so 10,000 RU is the science. Does the science look reasonable? It's not a big risk for the allocations committee to hand out those kinds of awards, but discovery level awards are a different thing. So these are peer reviewed. Standard are actually only reviewed by the committee, but major and discovery awards go out for peer review, and so we'll ask other people in your field to review the proposal and tell us, yeah, this is reasonable, or no, it's not, and why. And then Statewide Users Group actually does the awarding. And you guys, if you're principal investigators, you can participate in the Statewide Users Group, including the allocations committee, to help make these decisions and govern how OSC is used. There are also classroom accounts that can be gained this way as well. Those typically we just want to know what's the class, what's the syllabus, how many accounts do we need. We can get that set up. There's an important site, my.osc.edu. You will go to this site every 90 days or so to change your password. We do have a 90-day password expiration. That's I think everybody would like longer durations for those, but the nature of running a service with secure data, PHI data, and things like that, we have to do certain things to be in compliance with the requirements of the institutions that we serve. So my.osc is where you can manage your identity, so you can update your email, change your password. If you've forgotten your password, you can recover access to your account here by putting in your account name, and it will send you an email. You can change your shell, right? So by default, everybody gets bash, but if you want T-shell, you can change that there. And more in the future, and by in the future, I mean 2 weeks from last Tuesday. We're rolling out a new portal, which includes project reporting, authorized user management, requesting services. So a lot of things that you would do either at the command line or only through contacting OSC help will be able to be done on the web. So one example of that is getting your first account. You just go and sign up and request access to your advisor's project. Whereas currently someone would have to send an email to OSC help to ask for a project. We have to verify with the PI that yes, this person should be added, all that kind of stuff. And reporting is much easier now too. If we have time at the end, I can pull this up and show it to you if there's interest. Your contact information is important. We need to know who you are. So use MyOC to manage your account details to make sure that we have a correct email address from you. If you leave your institution but are continuing to collaborate, you can continue to use the account, right? If you're still working with your advisor after you've graduated or moved on, that's fine. We just need to make sure we still have a current email address so we can contact you about password changes or other issues we want you to reach out to you about. One common way that we use this is if an account is causing problems, if jobs are malformed or impacting other users, we'll look up who that person is and try to reach out to that person to talk to them and say, hey, how can we help you fix this? If we can't get a hold of you, we'll just lock you out, right? So better to, best that we have good contact information. System status. So there's a couple of places to look to see what's going on at OSC in terms of the status of all of these systems that we run. Currently, message of the day is the best spot. That's displayed at login, right? It kind of scrolls by. We do kind of keep that up to date. Also, an on-demand message of the day will be displayed on your on-demand dashboard. We have a Twitter account that is purely for systems issues. So HPC notices. If you're on Twitter, you can follow that account, and we don't put any media press releases out on that. That's just for systems issues. So there's no fluff on that. And an email. If we know of a scheduled outage, we'll send you an email about a month in advance to say, hey, the system's going to be going down on this day, so you can plan for that accordingly. If we have unexpected outages, we will also send emails so we keep people in the loop as to what's going on. scheduled downtimes. We have quarterly maintenance, typically one-day outages. We've done a good job of trying to do as much maintenance as we can on the systems while they're up and running, but there are some things that we just have to take the systems offline to do. So we try to schedule those about 4 times a year. They're held up for about 2 weeks prior, right? So if a job can run for up to 2 weeks, and I'll talk about scheduling limits a little bit later, I think. If the job won't finish before the downtime starts, we'll just hold it until after the downtime. And so you'll start to see scheduling get weird up to 2 weeks prior to the downtime as jobs start getting held. Our next downtime is actually the 23rd. That is when we do plan to roll out that new client portal as well. I've talked a little bit about the statewide user group already, but it's made up of OSC users, right? So the users provide program and policy advice to us, right? So we'll ask questions about how we're doing and how our resources are managed and what we're buying, and we get some feedback from this group about how we're doing on that. We meet twice a year. There is a chairperson elected yearly. As Amy mentioned, Tom Beck was the previous chair last year. The current chair is a chemistry professor at OSU named John Herbert. There's several standing committees, allocations we've mentioned before that do the allocating process. There's a software and activities committee that is responsible for making decisions about software licenses that we buy. And then hardware and operations, which is where we largely talk about the systems that we're going to build out. So this slide needs to be updated. Next meeting will be in October. It was actually last week. So next meeting is actually going to be in April, the next time around. And one thing we should mention about these meetings are an opportunity for you to present what you're doing as well to other users at the center. So we have flash talks and poster sessions associated with this meeting. We usually bring in a large prominent speaker. So we had the head of HPC sales, I think for the central region from Intel at this meeting last week, where he's talking about the Xeon processors and the futures that he sees for that, including quantum computing. It was an interesting talk. We haven't picked the speaker for next year yet, but we've had folks from NVIDIA and Dell and Intel have all come out recently. One of the things that really helps us out is if you cite OSC, we would ask that you, in the publications that you generate related to the work you've done at OSC, that you cite us. This helps us talk about impact, right? So state gives us money, and then they ask us, what's the impact of this money we gave you? What have you done with this? Well, we can point at hardware, but that's not really the impact, right? Or the state doesn't really care about the jobs that are created at OSC. My job is not important to the state. What's more important to the state is what is the science being done by these supercomputers, by the researchers using these? Who are all the people that are leveraging these services? And so this is one way to tell us about your story, is to just cite OSC so that we can go look those up. And it's more helpful if you tell us about it too, but at least if you cite it, I can find it, right? I can find citations in Google. If you tell me about it, it's even better. If you tell me about publications outside of your normal publishing routine, like Nature articles or being featured in the newspaper, those are great too. I like to hear about those. All right, let's move on to user environment. So there's a lot of commonalities between many HPC centers. None of you have used HPC before, but what you learn here will be applicable to a lot of other places you might go in the future. So we run a Linux operating system, right? It's a Unix-like operating system widely used in HPC. Have any of you used Linux before? Familiar? You Windows guys? Mac? You're going to need to learn a little bit of Linux to get around at OSC. It's kind of unavoidable. We've done some things to make it easier, but power users are going to have to get familiar with the command line and get familiar with using Linux. Mostly command line. We do have graphical user interface capabilities, which I can show. You have your choice of shells. Like I mentioned before, Bash is the default. We have several other supported shells that you can choose from. We have If you want to use an unsupported shell, that's fine, but we can't promise anything's going to work, and we're not going to support it if it doesn't. The operating system we use is actually Red Hat Enterprise Linux, right? So these are freely distributable open source software. There are lots of tutorials about how to use Linux available online. So we will often talk in some of our training classes about some basics, but there's so much good content out there that it's probably more efficient for everyone involved for you guys to go out and look at some of that content than for me to try to teach you. So to connect to the clusters, this is the kind of standard interface, right? So this is the way most people connect to HPC clusters. You SSH in. This is super simple if you're on a Linux machine already or a Unix machine already. You just type SSH user ID at oakley.osc or ruby.osc or pitzer.osc. .edu, and that will connect you directly to one of the login nodes that we talked about earlier. From a Mac, also pretty easy, right? You can open the terminal and just SSH to the machine, same as you would on a Linux or Unix machine. From Windows, the story is not quite so great. You're going to need some additional software, and there are commercial and free software packages available. We have some recommendations on our website as to what you can use to connect to OSC. However, you can go to OSC OnDemand and connect that way as well. And that's the easiest way because it works from any computer exactly the same, any modern web browser exactly the same. It doesn't require anything other than like Chrome or Firefox or Edge. I think it works. Yeah, it works in Edge. So any kind of modern browser will do. If you need graphics, if you're going to run MATLAB, for example, and you want to be able to generate graphics, you can run MATLAB without a GUI, but let's say you needed to create some plots or something. Super simple on Linux and Unix and Mac again. Just use a -X flag when you SSH, and that will do X11 forwarding and draw the graphics back onto your machine. I think on Macs you still need an extra piece of software, but it's super easy to install and it's free. Windows, same story as the last slide. You're going to need some extra software. Again, we have some recommendations on our website. There are commercial and free versions available. You have to do some configuration in the client to get it to work. It's not quite so simple as just putting a -X and having it work, but it can be done. You're going to primarily do this when you're working with programs on the login nodes. However, you can connect all the way through to a compute node and get those graphics forwarded all the way back to your machine. It can be done. We have some documentation on how to do that. OnDemand also makes this a lot easier. So let's talk about OnDemand for a minute. OnDemand.osc.edu is the place to go. Your temporary accounts will work there. It's a web-based user interface. So computers, tablets, smartphones, I have seen people, I've done it myself, log in to OnDemand on my cell phone and get a terminal or a desktop, and it's weird, but you can do it. Zero installation, right? So we used to require Java to get this to work, and that's not even required anymore. It's all done in HTML5. It's super slick. So it's a single point of entry to all of OSC services, right? So all you need to do is go to OnDemand. You need to know your username and your password. You're in. We do have a bunch of interactive services available there. File access, so you can manage your files via a web interface, including edit, upload, download, rename, kind of basic file services. Job management, you can actually create and submit jobs. So instead of going to the terminal and having to do all this stuff manually, we have some tools that allow you to create and submit jobs via the web interface. Visualization apps, so you can just get a desktop if you want it. So if you want a Linux desktop to work from, we can give that to you. We also have single-click apps, so Abacus, Ansys, Console, ParaView. If you want to use one of these software packages, you can just go to the apps menu and select it. It'll pop it up. You're good to go. Excuse me. And terminal access. So you can actually just open a terminal, right? So from a Windows machine, if all you want to do is get a terminal and you don't have the client installed, you go on demand, pop open the terminal there and do your work. So super easy. OSC.edu/ondemand has all kinds of documentation about how to use this, including little video tutorials of all the different tools that are built in. Highly recommended. And like I said, I'll pull this up and do a little bit of a demo later. Transferring files to and from the cluster. Most file transfers to and from OSC machines use SFTP or SCP. Linux and Mac have those built in. Super easy. Windows, you're going to have to get additional software again. FileZilla is the recommendation here. Super easy to use. For small files, you can just connect to a login node. So you remember those login nodes had those compute limits of 20 minutes? Well, SCP and SFTP encrypt files, which means they have to decrypt them at the other end. That takes CPU time, so if you're uploading a really large file, you're going to hit that CPU limit. But small files are fine. You can just move those right to the login nodes, no problem. For large files, because of those shell limits, you may hit failures, so you can connect to sftp.osc.edu just to move files up and down. That host is available. If you're on OnDemand, you can drag and drop files. Those are supported for up to 5 gigabyte files. So if you need to upload something larger than 5 gigs, OnDemand's not going to work. You're going to have to use an SFTP client to do that transfer. But for small files, it works fine. We need to talk about file permissions as well, right? So file permissions are your responsibility. You are responsible for maintaining permissions at a level you want for your data visibility, because other people in the system can see your files, right? By default, because we're an academic center, for academic accounts, everything is what we call 755, right? And so if you're not familiar with Unix permissions, it's basically they're octal sets, and it's the first number is the read, write, execute permissions for the file owner. The second 3 are read, write, execute bits for the group that owns the file, and the last 3 are read, write, execute bits for all the other users on the system, basically. So by default, 755 means the owner of the file can read, write, and execute what's created. And so directories get that by default. You need to be able to execute a directory to open it. The other users in the research group that owns that file can read and execute, but not write. So they can't change the file, but they can look at it. And by default, any user on our system can read and execute, but not write the file. So anybody can look at your files by default. So if you want to lock that down, that's up to you. You can use chmod to change those. There's documentation on the web. There's lots of documentation on the web about how to manage user permissions, but it's just something to be aware of. If you need to lock things down, you can. All right, so we've talked about the real power of the supercomputing being all of those nodes that you access via the batch scheduler, not the login nodes that you get to right away. How do you do that? And why do we do that, right? What's the purpose? Well, we queue jobs because it would be total chaos if we didn't. So if you can think about this right now, if the 4 of you all logged into our supercomputer and there's 240 nodes, and you just want to pick a node to go work on, I'm going to go log into node 198. Well, if there's only 4 of you, and those are the only 4 of you using the system, and there's 240 nodes, you're probably not going to have a collision. But in reality, there's 700 users using our system, and 240 nodes. You're going to bump into somebody. And so to make sure that we can guarantee that you're going to have the resources that you need, we have a scheduler that manages allocating those resources. So you submit your jobs to the scheduler or to the queue. They go into this queue. It's not really a first in, first out queue, and I'll talk about that, I think, in a minute. But then the scheduler will then try to pack those as efficiently as they can into the resources that we have available. So your job might run quickly. I mentioned 78% of all jobs start within an hour, but they might not, depending on what you're asking for and what's available on the system. And that lets us use the system much more efficiently than we would be able to without the scheduler. So compute nodes are allocated through the batch system. at OSC, we use something called PBS, Portable Batch System. The components are Torque and Moab. Torque is the resource manager, Moab is the scheduler. So Moab decides when and where you're going to run based on your request. Torque actually manages those resources to make sure that you have exclusive access to them, and that when your job is done, you no longer have access to those resources. We have a lot of really thorough documentation on our web at that URL. You can read through all of the stuff around batch scheduling and how to do advanced things with the scheduler. So every supercomputer center has some sort of scheduler. They don't all use PBS. They may use different resources. The syntax will be similar, but a little bit different, right? So the concepts will translate, but the exact syntax may not. So, all right, so what's the idea behind this? So we know why we do it. What's it actually do for us? Like, how does it work? Whatever you normally type to the command line will go into a script. That script will then be run at the time your resources are available, right? So you just think, I want to do this, then this, then this, then this. You would type those things interactively at a command line, store those into a file, give it to the scheduler. Scheduler will run that at 3 a.m. when the resources are available for you. You don't have to be involved. Output that would normally go to the screen will be logged into a file that you'll be able to read later. The system, like I mentioned before, runs your job when the resources become available. So it's very efficient. So how do we do this, right? So we create a batch script for that job, right? We create the text file that contains all the commands we want to run. We submit that. It pops into a queue. The scheduler figures out when to run that. And then the scheduler will pull that script out and execute it at the resources we want at the time that those are allocated to us. And you come back later and you get your results. All right, so there's a couple of things that we need to do to make this work. One is specify resources. So I have to tell the scheduler, what do I need, right? How many nodes, how many cores? Are there memory requirements? Do I need GPUs? How long do I need these things for? So wall time is a particular concept that's important. Wall time is the amount of like real world time that I need this node for, right? So the amount of time that clock on the wall ticks around while you're using the resource. You want to overestimate slightly, because when you hit your wall time limit, if you ask for an hour and your job runs for an hour and 1 minute, when it hits that hour, the hook is coming, right? The scheduler is the resource manager is going to say, you're done. I'm going to pull you off that node, kill all your processes, and your work wasn't finished because you needed another minute. So overestimate a little bit, right? Give yourself a little bit of a cushion so that if there's a little bit of variability in your processing time, you're safe from being killed. If you can't, for whatever reason, if you're bumping up against maximum wall time limits, you want a checkpoint. You want to save your state so you can restart that job. And actually, checkpointing is something that's going to be really important in Pitzer, because we're going to have the ability for you to run on a scavenger queue that uses the resources. You get the things more quickly, but your job might be killed at any time. So if you can checkpoint, you can get resources at a cheaper cost sooner and just restart that job and pick up from where you left off. So I'm not going to talk too much about checkpointing here because it's new, but shorter jobs may also start sooner due to backfill. So I mentioned the scheduler is not first in, first out, the queue. If I know I have a big job coming up that needs 40 nodes, and I'm not going to get those 40 nodes for another 2 hours. I have some of them available now, but the other ones there are other jobs running that won't be done for a couple of hours yet. I can take small jobs and run those on those nodes that are currently available and not delay that big job from starting, right? So I can jump over other people in the queue with small jobs. So shorter jobs may start sooner. So if you can break your work up into smaller chunks, you might be able to get little pieces of time much quicker than you would otherwise. This is really similar to the idea of the preemption, right? You're willing to work in smaller chunks to run sooner. I need to know your project number. I need to know who to charge this job to. And software licenses, because those are also a scarce resource, just like the compute nodes. Some licenses we have more than enough. We'll never run out, so we don't care to count this. Some other resources, we only have a handful of licenses. And so to make sure that you have that license when you need it, you need to tell the scheduler, this is one of those resources I need. So if someone else is using the license, we won't schedule your job to run and then have a license failure. We can wait. So this is an example of what that batch script looks like. At the top, we have the job setup information for PBS. So that pound PBS is the keyword that tells the scheduler, hey, these are lines that you should be interested in. We're giving the job a name. We're requesting a wall time. We're requesting nodes and PPN. And in this case, so one node, 28 processors for that node, and one GPU is in this particular instance. We're providing the job code to charge against, the project code to charge against. We're telling it that -JOE, that's going to take the output and the error streams and smash them together into one file. By default, they get different files. But if you wanted them in one, you could do that. We're requesting a software license. By the way, those are not ones, those are dash lowercase l. So those are for resource requests. And so we're also asking for one token of Fluent software. That's a CFD code. And now we're going to have our script. So after we've requested our resources, we're going to have our script. We've got some comments in there, some commands to be run. So we're going to load a module. I'll talk about that in a minute. We're going to change to this PBSO worker. That is the location on the file system where you submitted the job from. So it's a shortcut that jumps right back to that location inside your home directory or your project directory. Wherever you were at when you hit QSub, jumps right back there. So if you go to where the data is and you submit the job from there, that jumps you right back to that location in the script. We're going to copy an input file to temporary dir, so that's that local scratch space on the node. We're going to then change to that location. We're going to run Fluent and pass the input in. The results are going to get written out to that same directory on the local scratch space on the node. So then at the end, we're going to copy the results back to our home directory or wherever we submitted the job from on a persistent file system. So you put all of this into a file, and then you submit it by typing qsub in the file name. And that's all we have to do. At that point, it goes into the queue. You get a job ID back. So job ID, that machine name, that's our unique identifier. So if we need to look up this job later because there was a problem, we need to know that. It'll also be in the output file. It'll be job name, whatever you named your job, .o in the job ID. So that's a unique identifier that lets us keep track of jobs. You can look at the status of any job, qstat-a job ID. You can look at all my jobs, qstat-u, your username. And qstat-f job ID gives you a bunch of extended details. Again, this is all documented on our website, all of the options that you can use to kind of control and monitor what's going on with the batch scheduler. We do have some limits in place to keep in mind. Wall time limit, 168 hours for serial jobs. A serial job is not a single core, it is a single node. So we consider any multi-threaded application that doesn't actually cross to multiple nodes a serial job. You use up 168 hours for one of those. Right? So one core, or on Pitzer, up to 40 cores on a single box serial job. 96 hours for parallel jobs. The reason the wall time is shorter is that the risk of being impacted by failures goes up as you add nodes, right? Stuff fails on these systems all the time. And so to reduce your odds of you having a failure, we want you to shorten your wall time on parallel jobs and checkpoint. And so 96 hours is the maximum. We do have then user limits. We haven't set these for the new Pitzer system yet, but they'll be similar to this. 128 concurrently running jobs, up to 2,000 processor cores in use, and up to 1,000 jobs in the batch system. So you can submit up to 1,000 jobs at a time. Once you submit 1,000, we're going to, because otherwise somebody might dump 10,000 jobs in there and kind of break the scheduler. It just takes too long for it to work with that many things to go over. And then research groups also have limits. 192 concurrently running jobs and the same number of cores as the per user limit. So one user can use most of the jobs and potentially all of the cores that a research group can use at any one given time. And we put these limits in place to make sure that nobody just sucks up the whole system, so that everybody using the system can get their work through. You're going to have to wait for your jobs to run. Like I said, most wait times are fairly small, but it varies quite a bit. So if the system is very busy, queue waits are going to go up for everybody. Depending on the resources you're requesting, if you're requesting one of those large memory nodes, there's only 16 of them, right? They're a scarcer resource. You may have to wait longer for those jobs to So that applies nodes, cores, memory, GPU, software licenses. The more scarce it is, the longer your wait might be. Or the more that you're asking for, the longer your wait might be, just because it's harder to get those pulled together for you to run. I mentioned output goes to jobname.o job ID. That'll get copied back to the working directory that PVSO worked there, wherever you submitted the Q sub. That's where the output will be. We talk about Q peak. That's only really applicable on the older systems. On the newer systems, that file will be created in that directory. It used to be created out on the file system, and you had to run a command to look at it before the job was done. One thing to note is the very end of that output file will have a summary of the resources you requested and used and an estimated charge. So look at these when you're running, especially when you're running in parallel. If you're expecting to be using a bunch of cores and your CPU time and your wall time are close together and not wide apart, right? Because CPU time is how much processor am I actually using in my job. Wall time is how long did my job run. If I'm using 40 cores for an hour, I really want to see something closer to 40 times the wall time and the CPU time and not 1 times, right? If it's 1 times, your code's not working right. You're wasting resources and you're charging yourself more than you really need to be charged. So these are good things to look at to just kind of, does it look okay or does it look wrong? We can help interpret these numbers if you need the assistance. We have interactive batch jobs as well. So they're just like normal batch jobs, and they're handled through the batch system, so you will wait when you make these submissions. But instead of running a script non-interactively, like while you're off doing something else, it will just bump you to the command line on that compute node when your job starts. And then you can work on that node. You have a full, whatever dedicated resources you ask for, they're yours to use as you want at that time. The problem is I don't know when the time's going to be. Right? And the scheduler does not know. It doesn't tell you when your job's going to run when you submit it. So this is a little bit risky, but there are use cases where this makes sense, especially debugging parallel programs, or you're running a GUI that's just too big to use on a login node. We hope to make this easier to use in the future so that you can schedule the time that your interactive job runs rather than just waiting in the queue. To submit an interactive job, this example here, a -I is the flag you tell QSub, and so instead of running a script, it will just dump you out on the command line. We're going to do -X for X11 forwarding. We'll request 2 nodes, 28 cores per node, so 2 full nodes on Owens. We're going to ask for 1 hour of wall time, and we're going to ask for mail. That -M flag is sending mail. So this will send you mail when your job is ready to run. And some other, you can, again, read the documentation. It's all very well documented as to how to use that option as well. So that way you can do the Q sub and just look for mail on your cell phone and go back to your computer when your job starts. Other notes of import. 3 clusters have 3 separate batch systems. So if you want to run a job on Pitzer, you need to be logged into Pitzer. You can't submit a job for Pitzer from Owens. So submit and check status on the same cluster. Debug reservations exist on all of these clusters. A few nodes are reserved for short jobs, less than an hour. You have to request this with the -Q flag. So just like any other resource, when you're making your batch job submission, put -Q debug. That will route you into the debug queue. And those are kept open from normal running jobs so that they have really fast turnaround times for testing. Because if you're compiling and testing code, you don't want to have to be waiting 40 minutes for your job to run. I've alluded to this earlier as well. Each processor is fast. Real speed comes from using multiple processors. So multi-threading is becoming more and more important as we get higher and higher core counts. So use multiple cores on a single node. Shared memory, super easy. If you're writing your own code, there are libraries to help you parallelize this just with some pragmas if you're writing in C. Very, very easy. Most applications take advantage of this natively now. The other one is message passing, MPI. This is the way to get that distributed memory we mentioned before across multiple nodes. It's a lot more work though, and it doesn't come for free. So to take advantage of parallel computing, your program must be written to take advantage of multiple cores, multiple nodes. Many commercial applications do have multi-threaded or parallel versions available. So if you're using commercial code, check the documentation to see if it can support multi-threaded or multi-node. You must use MPI exec to actually take advantage of these multiple nodes. It sets up the environment for the message passing interface. You can't just request more nodes and cores and expect your job to parallelize. We see it happen all the time. People do this, and it just doesn't work right. So let's talk about software. We use modules to manage our software environment. They allow us to have multiple versions of MATLAB available, for example. I can have 5 or 6 different versions of MATLAB installed, and they don't conflict with each other. Or other packages, right, maybe conflict. I can use the module system to make sure we have a coherent environment for users that are using different software packages. We do have a default set of modules loaded to login. A module system and batch system are 2 of them. Do not unload those because those are important to keeping the system working itself. But we also provide a default compiler and MPI modules, the ones that we recommend. You can change those, feel free to. If you want to install your own software, we have lots of instructions about how to even write your own modules and have your own module system if you want to do the same thing. But if you just want to install something and modify your path to point at that, you can, that's fine. Just don't completely replace your path in your bash profile or bash RC or all this stuff that we install breaks for you. So prepend, use the prepend instructions here to modify your path. So how do modules work? You just load the module you need, right? So module load console will bring we choose which version is the default, but it will bring a version of console into your environment for you to use, and you can just type console and off you go. If you want a particular version, you can do console / 4.1 or whatever, and select the version you need. By using modules, we can also tweak how things work kind of behind the scenes that you guys won't see. So if there's a change or an error in the environment, we can make a change to the module. None of your scripts or codes change, but things work better. We fix whatever the issue was. So don't hard code paths. Don't look at where console 4.1 is and just run it, because we may make some change to the environment that would break that for you if you don't use the modules. You can load modules at the command prompt. You can put them in your bash profile or bash RC. You can actually load up the modules you want and save that as your default environment in the modules system. There's documentation on how to do that. And you can load modules in your bash script, so you can get the exact software environment you want. To see what you have loaded, module list works. You can module spider or module avail to see what things can be loaded. So for example, I can do module avail Intel to see all of the versions of the Intel compilers that are available. I can do module load CUDA to load the default CUDA environment in. I can unload a module by module unload, so I can unload the Intel compilers by module unload Intel. Or I can change software versions. So if I want to change from the default version of the Intel compiler to version 13.1.3.192, I can just type module swap Intel and then the version I want to replace it with. When you do some of these things like unloads and swaps, there may be dependencies, and the system will automatically manage those for you. So if you change your default compiler, we will change your the MVAPitch, the MPI library, for you to be compatible with the compiler. We have a bunch of software available. There's actually, if you go to the website and there's a resources software, you can see the full list and filter that list by academic discipline if you want to see what we have. This is a partial list of general programming software that's available. Parallel programming software, I mentioned MPI libraries. MVAPitch is the default one that we use. We have others available as well. OpenMP, CUDA, OpenCL, OpenACC are all supported. We have some license that has restricted access. So most of our software licenses are only for academic use. If you're a commercial user, you're going to have to buy your own licenses. Some packages require a signed license agreement, and that'll be documented on the website. So if you need access to a particular software license, it may be restricted by institution. Most of them are statewide. It may have a license form that the user and the PI have to sign to and agree to. So check the website, contact OC Help if you need access to one of those. And there's the URL actually for the software page. If we don't have it, we can get it. So if there's commercial software, fill out a request form and sub will consider it. We do have money set aside to buy these statewide licenses. If it's something that can be used by multiple institutions, it makes a lot of sense for us to buy it. Open source software you can install yourself, but again, if there's enough demand, we will install it centrally and maintain it. If you have your own license for software, contact us. We can help you get that running at OSC. It may require a license server. We can either run one for you or point back to an institutional license server if you have one running here. To get help, these are some resources. So the FAQs are pretty good on our website. We have a bunch of how-tos, which I think are great, explaining how to do some of the more complicated but frequently asked for operations, like, for example, installing your own Python libraries that are compatible with our Python environment. Got instructions on how to do that. We have a new user resource guide. This usually gets sent to everybody when they get their account information, but it provides links to all the most commonly used portions of the website. Updated presentations are available at that location. The copy of this presentation is actually available back at the OSC website at the calendar entry for this event. So if you go back to where you registered, you can find a copy of the slides if you want it. We have office hours. These are actually at OSU, but we can do WebExes, right? So we don't have to come down here every time if you want to talk to somebody. There are some local resources. You can talk to UCIT, you can talk to Brett, local campus champion. But you can also talk to us, and we can do WebExes if something like just sending through the ticket system isn't really going to work. Remember to check system of the day or message of the day. Follow HPC notices if you're a Twitter user. Any questions? Okay. I want to pull up OnDemand real quick if I can. We're right about at time, but I'm going to go ahead and pull up OnDemand if that's all right. Maybe. There we go. Okay. So you can log in with your OSC account or through CI logon. So you can actually tie this. Does UC have CI logon? Yeah. So you can tie your OSC account to your campus credentials, which means you can log in via the kind of one-time sign-in and have that propagate to your on-demand sessions. So that can be a convenience for you. I'm just going to log in with my OSC account here. And I'm going to put in my username and my password. Excuse me. All right, so I'm now logged into OnDemand. You can see right here we have an old message of the day that probably needs to be removed. I'll have to look into that. But basically, you'll get message of the day here. You'll get access to HPC services, so you can go to, I can look at all my file locations on the file system or my home directory, and this pops open the home directory tool or the file management tool where I can edit or upload, download files very easily. There's a job composer, which I'm not going to do a full demo of, but I will show it briefly. I can basically create jobs from templates, right? So we have some basic templates here. You could pick one of these, but I want to run a parallel R job. I can select this template, and it shows me what I get, and I can copy that and then modify it. Or you can create your own templates and then reuse those. And this gives you a way to avoid the command line, but still manage your jobs. And I can submit those. I go back to jobs, and I can see, like, I ran this job back on March of last year, and I can look at my output, like, right here, and see kind of, this is just an MPI, hello world MPI process. But so I can manage my jobs and look at my output and all that stuff via the web if I want. Again, we have a lot of good documentation on the web on how to use the job composer. I can look at active jobs. This is handy if I have jobs running. I can go here and see my jobs, but I can also look at my group's jobs, which is probably none. Oh, no, there's one. So I can look at this job that's running and see performance information of the job, including memory usage and CPU usage. So I can look at my own jobs and check their performance kind of as they're running. We hope to eventually add the ability to look at historical job information this way as well. I don't have that currently. We don't store this stuff for long periods of time. Other things that are useful, I can get a shell, right? this is not super exciting, but I can log into Oakley right here, and I've got a shell, and I'm ready to go. And I can do like a QStat to look at the status of the queue and all, directory listing, all the things that you might be able to do, in a normal SSH session. Perfectly fine. I'll leave that. I can also look at system status. So I can pull up and see, okay, here's, Pitzer's not very active because we're just testing it. We don't have users on there yet. But the other systems, you can see how many nodes are in use, how many processors are in use, how many jobs are running and queued. So there's 329 jobs waiting to run on Owens right now. None on Oakley, and Oakley's a little underutilized at the moment. So if you wanted to run like right now, you can look at this and say, oh, I should go to Oakley, and I should go run that. And then I can drill down to, if I wanted to look at Owens in more detail, I can look at the overall node utilization or job performance, number of jobs running, and over the last hour or last week, whatever. So there's a lot of information that we make available via OnDemand, and then there's the interactive apps. And so I'm just going to request a VDI desktop. So VDI is a shared desktop. The Owens desktop is a dedicated desktop, so it depends on how you want to use this. Or one of these basic apps. We have RStudio, Jupyter Notebook, and then some of these other MATLAB and things like that. I'm going to go request, actually, a Oakley VDI. I'll do an Oakley VDI. I got to put in my account, which I don't remember, so it's going to give me an error. Yeah, I'm just going to launch this. So this is just giving me one core on one node. I do not have an account code set, so let me grab one. So because I have multiple accounts I can charge against, multiple research projects, I need to specify which one. So if you only have one, it can make an assumption, but if you don't, you have to do that for it. So now I'm in the queue, waiting for this to run. Just like any job, it goes into a queue. I've requested 8 hours on one node. There, I'm already running. It didn't take very long. I can launch no VNC. And now I have a desktop running on Oakley, and I can do all of the things I'm running on a compute node on Oakley, and I have access to that just like I was in the normal batch system. So if I need to run GUIs interactively, this is a really good way to do that. So I'm going to delete this job now because I don't need it. I can free it up for somebody else. But yeah, so that's kind of a really basic introduction to OnDemand and things you can do in it. So it makes it a lot easier. The barrier to entry is lower, and this is really, really popular. More of our users use this than traditional SSH now. That actually crossed over sometime last year. And this is now about 2/3 of our users connect via OnDemand and not via the command line. So that's all I got. We ran a few minutes over. Any additional questions? All right. Well, feel free to contact OSC Help if you have questions or need assistance, or the local support folks, and we can all try to get you up and running and get you productive on the system, make sure your research is going well. So, all right, thanks.